So our next type of integration is going to be integration using partial fractions. So partial fractions, just to give you an idea, is we're trying to take a fraction and reduce it down to a sum of kind of easier fractions. So that's kind of the idea, is that I want to take this complicated fraction and rewrite it to be a sum of simpler fractions. So for example, and I think this is easier to jump right into an example here, we're trying to figure out the antiderivative of 5x minus 4 over 2x squared plus 2x minus 1. So first thing when I'm looking at this problem and I'm trying to integrate, I want to say, can I use u substitution? Well, if the top said 4x plus 1, then I could, right? Because then I would be able to use the derivative of the bottom was the top, use u substitution. But I can't do that. So what I'm going to do instead is I'm going to try to use partial fractions. So the first step of partial fractions is you need to factor the denominator. So I'm going to need to actually split up the denominator as x plus 1 times 2x minus 1. For partial fraction decomposition, whenever you have a linear term, so linear term is x to 1 power, so not x squared, just x, you're going to decompose it as a constant over whatever that factor was. So that's the decomposition of a linear factor. So down here, what you notice is that I have broken this down into two linear factors, which means I'm going to break this fraction up as a over x plus 1 plus b over 2x minus 1. So I'm going to have a fraction for each of the factors of the denominator. Our goal is to find a and find b. Once we figure out those two things, then we will be done. We'll be able to integrate. But because I had two linear factors, I'm going to have two fractions. Each of the fractions is just going to have a number on top. So whatever you have on the top is always 1 degree less, unless you start having multiple factors, like if I had one of these squared, that's different. But if a linear factor is always going to have just a constant on top, if I had like an x squared, then I would have a linear term on top, that kind of stuff. So we've, like I said, written this. We're going to go for a over x plus 1 plus b over 2x minus 1. So once I split the fractions together, my ultimate goal here is to get what is a, what is b. So we split up the fractions, now let's put them back together and see what we get. So I'm going to just ignore everything over here, ignore all that. What happens if I put these back together? So if I put two fractions back together, you got to multiply the denominators. So I need to multiply this first fraction by 2x minus 1. And I need to multiply the second fraction by x plus 1. Over x plus 1, 2x minus 1. And then I'll combine them now that I have my common denominator. So I'll get x plus 1 times 2x minus 1 is a times 2x minus 1 plus b times x plus 1. Okay, so we split up the fraction as a over x plus 1 plus b over 2x minus 1. Then I put them back together, and this is what I got when I put them back together. But if you notice this first fraction, the one I told you to ignore for a minute, and this last fraction, they have the same denominator, which means the tops of these fractions have to be the same. So I can set 5x minus 4 equal to everything on top of this fraction, and that's what you see here. Next, I'm going to actually distribute the a. So I'll distribute my a and get, what, 2ax minus a plus bx plus b. So I distribute my a, distribute my b. And then the next step, and we're getting pretty close to the end of this, the next step is look at all your x terms and factor out an x. So I have x terms there. So I have a 2a plus bx. And then I'm also going to look at my constant terms, so the terms with no x's. So negative a plus b. And that's where this line came from. So I grouped all my x terms, I grouped all my non-x terms, and I put those together. Then you're going to set coefficients equal to each other. So if I go back here, what you notice is that whatever term over here is in front of x has to equal whatever term over here is in front of x. So I know that 5 is equal to 2a plus b. I also know the constant has to equal the constant. So I know that negative 4 is negative a plus b. And that gives me a linear system of equations. You can solve that system of equations. You can either use substitution, you can use elimination, whichever one you like best. But I get that a equals 3 and b equals negative 1. And that was my goal. My goal was to figure out what is a and what is b. Our a is 3, our b is negative 1, so I can go back and plug those in. So this is a 3, this is a negative 1. So instead of integrating this, we're actually going to be integrating this, the right side of the equation. And so let's do that. So we're going to integrate 3 over x plus 1. Well, that's a natural log, so 3 times natural log of x plus 1. Next, I'm going to integrate 1 over 2x minus 1. Now you might need to use some substitution to do that because this 2 in front of the x, so I need to have a 1/2 out front. So I'll have minus 1/2 natural log of 2x minus 1 and then plus c. So that's how partial fractions work. We start with a fraction. You want to kind of simplify it down, and then you want to integrate those simpler fractions. One thing we should say though, you have to actually have the top degree being less than the bottom in order to do this. So if I'm looking at this example, this 2x cubed minus 11x squared minus 2x plus 2 over 2x squared plus x minus 1. What you see is that the degree on the top is bigger, which means I can actually do long division, and I should do that. So if the top is bigger, the degree on the top is bigger, you should do long division. And if you've forgotten how to do long division of polynomials, that's okay. I'll post a video about that. But you need to do long division, and then you want to do the partial fraction decomposition. So always make sure that the degree on top is smaller before you try to do this. One thing, if you have 3 linear terms, so like on this one I have an x factor, x minus 3 factor, and a 4x plus 5 factor, that means that my partial decomposition is going to involve 3 fractions. Each of them is linear, so it's going to be a, b, and c for my numerators. If you have a term that repeats as a factor, so here you see I have x plus 2, which is linear. X plus 2 is linear, but it repeats because of this 2 as the exponent, as multiplicity 2. That means that I need 2 fractions in the decomposition. I'm going to need 1 for my x plus 2 and 1 for x plus 2 squared. If it would have been cubed, so like let's just pretend it was cubed, it would be a over x plus 2, b over x plus 2 squared, and then plus another c over x plus 2 cubed. So if you have something that repeats, so if it has a multiplicity of 2 or greater, you're going to need a fraction for each one of those multiplicities. For the x minus 1, it's just a normal linear, so it's going to be c over x minus 1. If you have a quadratic, so if you maybe can't reduce it down at all, then the part that goes on the top has to be 1 degree less. So 1 degree less than a quadratic is a linear. So your decomposition would look like ax plus b over your quadratic. And then to figure out the integration, you would go ahead and you would use inverse tangent.